I'm going to record. Sorry, that was probably a terrible noise, Nathan. Are we ready? Today we have a bunch of questions to start. Here. We have ethanol and dimethyl ether. Okay, cool, bro. But based on their structure and intermolecular forces account for their difference in boiling points. So we got one here that is 78 Celsius and one that's negative 24 Celsius. You have a discussion with your partner and try and answer this question. Why is one so much higher than the other? You don't have to do like every one of them.
I don't care to do all of them.
Okay. That one's gross. Does that go in? Oh. You're too nice to me.
What? Okay.
All right, how are we doing? Are we having good discussions? Okay, are we playing cool math games?
Always.
Sweet. All right, oh, you've moved. Thanks. Okay. So first off, which one of these has the higher boiling point? All right, ethanol. When you get two negative boiling points, sometimes you're not very good at negatives and you screw it up. Just gonna warn you right there. Remember, like negative 38 versus negative 11, which one's the higher? Negative 11. Yep. So.
What did you go with negative 11? Who said that?
What?
Wait, what?
Negative 11 is a warmer temperature than negative 38.
Oh, okay.
Okay, here we go. Yeah, it's tricky, right? In your head, because it just doesn't feel right. Okay, so this one's high, this one's low. Based on their structure and intermolecular forces. Well, what would their structure be? You don't have to draw it out, but I'm going to for a minute. What am I missing here? And then we got OH. Okay, then we have a pair here. So that'd be bent. Versus, so this is ethanol. And then this one is CO. It looks like that. Okay, we'd have two pairs. All right, so there's our structure, which you would not have to draw it out, but you have to understand it. This structure should show you the main difference. So why is this one so much higher? Hydrogen bonding. You can write the double bond, but make sure you write hydrogen bonding for sure, because that's the most important part here. This has hydrogen bonding. But wait, doesn't this have hydrogen also? All right, but there's no H ever connected to an NO or an F interacting with an NO or an F. What? Don't listen to Bert because he's wrong as far as the AP test is concerned. I'm not saying he's wrong in life, but AP is just NO or F. So are we all right with that answer? So you would say something that sounds pretty smart. You'd say that ethanol, since it has an OH interaction, would have hydrogen bonding versus dimethyl ether where the O's, or sorry, the H's are bonded to the C's. Something like that. Good? Okay, next. Okay. The structures of ethane and methanol are shown below. One of these two molecules is liquid at room temperature. Based on their structure and intermolecular forces, predict the molecule which is a liquid at room temperature. Ready, set. This shouldn't take very long. Okay, can anyone tell me what the wrong answer would be? Like this is tempting us. What's going to not be an explanation? Okay, that would be the right answer and the wrong explanation. He said the wrong way to say it is this one's a liquid because it has hydrogen bonds. Because it doesn't. What would be missing in this? An OH or ON or an OF interaction, right? That's not there. Okay, so it's tempting. You're like, oh, I see an O, I see an H. No, you don't. So can we agree that this one is probably the liquid at room temperature?
Yeah.
Okay. Can we agree they have the same molar or molecular weight is what it's called, or molar mass? Okay. So that usually, if they give you it and it has the same mass, they're trying to make sure you don't put what else as an answer. London dispersion forces. Is that what you said? Because they're going to have pretty much the same London dispersion forces. So what's the only thing left? There, it's polar, a dipole-dipole interaction. Okay, so we would say something to the effect that methanol is polar because the C to O double bond versus ethane is nonpolar. So this only has London dispersion forces. This has London dispersion forces and dipole-dipole interactions.
I actually thought that ethane would be the liquid only because I thought the other option was solid and not gas.
Okay.
So I didn't know it was.
Does this make sense now?
Yeah.
Okay. Yeah.
So, hydrogen bonds are pretty much just dipole.
Yeah, hydrogen bonding is a very strong form of dipole-dipole interactions. That was right there in our notes.
And it just exists, so like we have to make sure that if there is, it's like we just have another step.
Yep, checking if there's an O, H, an NH, or a FH interacting with an O or an F. Everyone alive? Okay. All right, so you would say, here's the like straight from AP. Ethane is a nonpolar molecule, so here. So it only exhibits LDF, while methanol is polar and has both LDF and dipole-dipole. Because their size is comparable, the LDFs don't matter. Methanol is a liquid and molecular forces are stronger overall. Fair enough. That's what we said. You feel comfortable there? Okay. This, a lot of my videos will have like 0 views, 1 view, 2 views, and then like 30. I'd encourage this one to be a 30 before the actual test. Because I'm going to ask these questions. Okay, they're going to be just like these. Let me cover that back up for next year. Huh. What? Calculate it? No. Well, there is in chapter 13, and 11 and 13 are put together just to celebrate my birthday. And it'd be a super short test if it was only 11 or just 13. The math in 13, most kids don't hate. It's basic algebra. There's no picket fences, if I remember right. It's just 12 is non-applicable. It's on modern materials or something like that, which the AP test doesn't test. It's actually really interesting, but no one's reading anything anyway, so it doesn't matter in the long run. Okay, this is different. Explain these two. Butane, -1 degrees. Methyl propane, -11.7. Explain to your partner.
It's something that
All right. Are you ready? What is this testing? LDF, and specifically a word that starts with a P. Polarize ability. Okay.
So what's it got?
Yep. Correct. Okay, now this was my foreshadowing. This is a higher boiling point right here, right? And this is a lower. So which one of these has higher intermolecular forces? All right, it's this one. The higher the LDF, the lower the boiling point. Or did I say that backwards myself? The higher the boiling point, I'm sorry.
Yeah, okay.
What did I just say? I said it backwards, so tell me how I should say it without looking.
Higher LDF, lower boiling point.
Here we go. I warned you guys and I fell for it myself. Let's just talk real quick. Look right here. This is a straight molecule, right? Which means it's what? It's more what? Polarizable. All right. Which gives it stronger LDFs, which means it has a higher boiling point. Yep, sorry about that. It's okay. I make mistakes. All right, are you okay with this summary right here?
Yeah.
The higher LDF.
All right. Yes. Okay, so we learned that straighter is more polarizable than not straighter, right? So we're looking for the fact that a linear or straighter molecule has more surface area to interact, thus it is more polarizable, which would give it a higher boiling point. We good with that?
Yeah.
Okay, sorry. That was the first mistake all year, isn't it? Just kidding. Well, I didn't realize I was about to punch you. I'm sorry. This is a good seat right here.
I know.
Like, why have I not always taught from here? Just noticed I look fat. So, all right, good. This one, if you stumbled onto this one, and it didn't tell you this, there's no way you'd know this. Okay, in the table below, the table below summarizes some physical properties of chlorine and hydrogen chloride. All right, now I know you are like, this is hydrochloric acid. That's not hydrochloric acid. It would have to say HClAQ for it to be hydrochloric acid. So this is just hydrogen chloride, and it is a thing. It's not an acid until you put it into water.
So it's just a solid?
It's not a solid. It's a gas. It's a non-polar substance. So it's covalently bonded, most likely, whatever. Okay, how can we use our understanding of intermolecular forces to account for the difference in enthalpy of vaporization? Okay, now what in the world is this? Enthalpy just means energy, right? Vaporization means to make it a vapor. So it's just saying the energy required to boil it. So what we're saying is it takes more energy to boil chlorine gas than hydrogen chloride. Now that, it should actually feel like that's a lie. What do we know about chlorine, Cl2? What type of bond is that? It's non-polar is the word I'm looking for. It's non-polar. Like its electronegativity difference is 0, right? And that's what this is. A dipole moment is essentially its electronegativity difference. Now, it's not exactly the same, but they're similar. But this one does have a dipole moment, which means this one is more polar, which means this one should take more energy, but it does not. The data shows you, and if the AP test gives you data, you must assume it's true, okay? Unless it was like student A and student B. So the question is like, why? Like, why? This does not make sense to what we know. So something must be winning here that we usually wouldn't say is a winner. Any ideas? No. But you know I love and appreciate you though.
The dipole is like so small.
And okay, you guys put everything the two of you just said together, and it's a perfect answer.
Bigger, so it's more
All right.
polarizability.
So based on this data, we must extrapolate this idea that the chlorine is much larger electron cloud, which means it is more polarizable. You with me? And based on this data, must be greater than the dipole interaction between H and CO. That's a lot of words, but the data proves it. Even though this one is more polar, this one must be more polarizable because it's much bigger. We have 36 electrons here. We have 70 electrons here. It's twice as big. Now, not mass and all that, like it's close in mass, but we're talking electron clouds here. So occasionally, when they're different sizes, it gets really hard to know which is which. And so you would have a table that tells you, hey, chlorine wins. That's what this number's saying. In our intermolecular forces battle, chlorine wins because it takes more energy to boil it. All right. So then you have to extrapolate why. All right. Well, even though it's not polar, it must have easily polarizable molecules that are greater than the dipole-dipole interactions. It's tricky. All right. Now, this is the key. I thought I had this highlighted, but maybe I erased it. It's right here. This term right here. They have to be comparable sizes to be just cut and dry, like those were. Those were both 30, right? So LDFs, I'm not worried that one has a way bigger polarizable substance. I care mostly in that one about the dipole-dipole. But since these were much different in mass and electron cloud, that matters more. Okay. This is one that's pretty weird as well. The table above gives the molecular structure and boiling points of CS2 and COS in terms of types and relative strengths of intermolecular forces in each compound. Explain why the boiling point of CS2 is higher than that of COS. If there was not a data table here, me, Tom Davidson, who's taught AP chemistry for 17 years, would have thought it was the other way around. I would have thought this was higher than this. Because in my mind, I would have thought oxygen, COS is more what? Polar than CS2. And I'll bet you 99% of everyone would assume that. But we have a data table that says it isn't. And we got cheaters trying to read. I'll make it smaller.
I already read it all.
Oh, crap. There we go. On my computer screen, it was impossible to read, but then it did get a lot
I have really
bigger.
bad eyes, so I'm surprised I was.
Yeah, I just underestimated how big this would be. Okay, so are we ready? It goes along with the previous slide. What do you think it must be? Sulfur is twice as big as oxygen. So we must have more polarizable, whatever. Okay, so CS2, what will we, does it say it up there? It doesn't. What will we call CS2? Tell your partner. Carbon disulfide. Good. I don't even know what we'd call COS because that's not really a thing. I like that. And it's equal to sine over, I don't remember, tangent over adjacent. Wow, that goes back to 1992. So don't ask me anything about trigonometry. That unit circle, which blew my mind. Okay. Carbon disulfide is nonpolar and exhibits only dispersion forces. All right, COS is polar and exhibits both dispersion forces and dipole, which usually would mean these numbers would be reversed, right? But we have to trust this data because AP gave it to us. See, source, College Board. They're not going to lie to you on the AP test in a data table. If they do, they'll be very clear on it. They'll say a student got trial 3, and that data could be trash because a student got it. Okay with that? Okay, but back here. However, so now we have to just reason through, like, why is this different than I think? It has to be because the electron cloud of CS2 is larger and more polarizable than that of COS. Therefore, the dispersion forces of CS2 are stronger than all combined forces of COS. Polar is a bond where there is actually like a movement of the electron to one side and away from the other. So you end up with two poles. We'd have the negative half of this molecule and the positive half of this molecule. Polarizable, there is no, this is called the dipole moment. In this, there is not a dipole moment, but we can get an induced dipole if we can polarize or make the electrons move to one side. And then the other electrons are attracted to the nucleus. The London dispersion forces. This is a really weird thing, like to really think that deeply about. Go ahead.
When it comes to the size difference, how much bigger or smaller is the molecule?
Well, that I cannot answer that, and no one will have that exact answer because it would depend on the types of atoms involved too. It would depend on their temperature. It's too much. But in AP, if they're going to test this specific thing, it would be a measurable amount, not like 2. This is 16 more, which isn't huge either, but it's a difference. So then the other one was 35 more. So there'll be a fairly significant difference. All right. In our notes, I skipped this unintentionally. Yes.
I don't want to try and be wrong.
It's okay. I appreciate that you are usually willing to step out.
Is it like a...
It's okay. So the AP video, and my chemistry teacher back in the day taught this the same way. In a lake, right? Pretend this is a lake. There are fish. And what do they breathe? They breathe oxygen through their gills, right? Right? They take water into their gills, and their gills extract the oxygen that is where? In the water. Well, that shouldn't work. Oxygen and water should never mix, theoretically speaking. So we must have something that causes there to be some small interaction between water and oxygen so that they will mix and stay together a tiny bit. Go ahead. Yep, this is between a polar substance and a nonpolar substance. And they're not very strong, and they don't last very long. Induced means one causes the other to have a momentary change. Okay, now that's not, when you go to have a baby, that's not what induced means. It means your doctor's going on vacation and wants to have your baby now. Okay, that's hashtag Derek Davidson. All right. But there is an attraction between this water molecule and this oxygen molecule. All right. It's, I don't know, it's kind of hokey to explain, but we're used to just weird crap, right? So what happens is we know oxygen's minus here in the water molecule, correct? That's what the S negative means. And it's not a full ionic charge, it's just a partial negative. Okay, so that negative will do what to the electrons in this oxygen? It will repel them. And if electrons move to this side, even though it was not technically polar to start with, becomes an induced pole that's negative. And then this, having abandoned its electrons, all right, the electrons abandoning it, I should say, is now just a nucleus that's unguarded, right? And there will be an attraction between this negative and the nucleus of oxygen. It's definitely not very strong, and it stops like almost immediately. It just is barely there, and then it's gone again. But if we remember how many things in 18 grams of water, we have 6, 0, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. In 18 grams of water, we have this many atoms or molecules of water. And a lake is way more than 18 grams, right? So even if like 0.000000000 whatever percent of these is going through that, that's still an unbelievable amount of atoms that are being induced, attracting, breaking, and as they're breaking, another one's formed anyway. That's how oxygen sticks to, or it doesn't stick to it, but it's how it's carried into the water environment, so that then the fish, it breathes this through its gills. It doesn't breathe it. It takes water through its gills, and with some of that water, the oxygen is attracted and travels through, and then the fish gills easily break this attraction and then use this to fuel their bodies. That's real smart. I wish I was as smart as you. Okay, are we kind of all right with that? So when a dipole of water approaches the nonpolar oxygen molecule, the electrons of oxygen are repelled by the negative part of water, and oxygen is forced to have a dipole or induced. Okay, anytime you see like these letters and then whatever, these are cut directly from the AP like book of what I have to teach you. So this is what we're looking for. Dipole-induced dipole interactions are present between a polar and a nonpolar molecule. These forces are always attractive, okay? All of these forces in this unit we're talking about are attractive, okay? The strength of these forces increases with the magnitude of the dipole of the polar molecule and with the polarizability of the nonpolar molecule. So AP likes to have you know how they change. So the more polar something is, and the larger or more polarizable the molecule, the more this would matter. Okay, so here's my question based on that sentence right there. Would this work as well if I substituted in what I need green right here? If this was a hydrogen and a hydrogen, is it going to be an induced dipole to water? It would be extremely small. What would it be then? No, because this hydrogen and this hydrogen are bonded to each other. So there would be a slight attraction here, but we would not call this a hydrogen bonding because this would have to be an N, an O, or an F in order for that to happen. Right. Okay, so an induced dipole dipole-induced dipole, it works well with oxygen because it's more polarizable than hydrogen would be. You okay with that? Okay, you all right? Are you missing your chair? You got a pretty good lab partner, so you're probably fine.
No, she's awesome.
She is.
I could still benefit from her.
He's not here to defend it. So, all right. This just says what we just said. When two polar molecules interact, we call it dipole-dipole. And we're used to that one. When one polar and one non-polar molecule interact, we call that a dipole-induced dipole. Uh-oh, what do we got going on here? I'm uncomfortable. Hey, what's up? Good. All right, we ready for the next slide? I think the next slide, I'm going to attempt to teach biology. I don't feel good about it either, okay? When you're like, I don't like this, know that I don't either. You inhaled before we even said anything. Okay, here we go. This didn't used to be on the AP test at all, but it is now. So it's just this little nugget right here. In large biomolecules, which 99% of the time they're going to say a protein. Okay. So in large biomolecules, non-covalent interactions may occur between different molecules or between different regions of the same large biomolecule. So this is weird because we haven't really talked about non-covalent interactions, but we've really been talking about non-covalent interactions the whole time. A non-covalent interaction is an intermolecular force. It means it's not a covalent bond. It's an attraction in a different way. Okay, so they affect the structure of these things. So for instance, and we don't have to know about hydrophobic in this class, but in this example, it helps. So in a hydrophobic substance, it doesn't like water. So what it will do is it will wrap itself around to limit the amount of surface area that's in contact with water. Hydrophobic, it doesn't like water. Okay, that is actually a non-covalent interaction. Okay, now we don't have to know that hydrophobic, but just kind of understand what's happening here. The reds don't want to be by water. So they fold inside and put the blues, which are hydrophilic, which means they like it, on the outside. So now most of the interaction between this molecule and the surrounding water, it's with the philics on the outside and the phobics are hidden on the inside. And it causes a unique structure for these proteins. You okay with that? Okay, so this is a type of non-covalent interaction. This one is not actually on the AP test. It's just an easy one to explain. Okay, a non-covalent bond in a protein, you can actually have an ionic bond. All right, and it's hard to see, but this N and this O in this protein like come together and help the protein stay curved or bent. All right, there's other reasons why it's staying together, but we can have an ionic interaction here, an ion or an ion dipole. All right, and then again in the protein, when there's some parts here and here where they will be attracted to each other between a hydrogen bond. Okay, and you don't have to know every single one of these. You just have to know that the structure of large biomolecules is affected by these intermolecular forces and attractions. Okay, so here is a zoomed in version of a protein fold. You all right with that? And I'm not going to go into a ton of details, but it started to bend because it is hydrophobic and wanted to be here. All right, as they come closer, there are van der Waal interactions. All right, we've talked about van der Waal interactions. Those are intermolecular forces, van der Waal forces. All right, we will get induced dipoles here. Up here, once again, there can be ionic bonds that form to keep this substance together. There, whoops, I circled the wrong one. This was the ionic bond. I apologize, NH3O. And then there is hydrogen bonding as well. So you don't have to know a ton here, except for you need to know the structure of large biomolecules like proteins is affected by many types of intermolecular force attractions. And they call them, to wrap this part up, a non-covalent interaction. A covalent interaction, like in this diagram, is the C bonded to two H's and bonded to that, right? These are covalent bonds. These are non-covalent interactions. We all right with that? Like, it's kind of weird. It's like the only biology pretty much on the whole 15 units or whatever that we're going to do. Okay, well, that's not true. There's a little bit on buffers, which is kind of interesting, actually. Oh, thank goodness for low pressures. Remember our weather lessons I've always given you? I can see the mountains out there. That means the inversion's gone. I've never taught you about the inversion, have I? Right now, go. Okay, pause video. You're welcome for Weather 101 by Tom Davidson. All right, summarizing intermolecular forces. All right, yada, yada. I don't know how useful this is, but are ions involved? Yes. Are polar molecules involved? Yes, ion dipole. If it's just ions, but no whatever, it's just an ionic bond. Okay. Now, if there are not ions, then you say, are polars involved? And then you'd say yes. Then you'd check for NO and F, and it's a yes, there's hydrogen bonding, which is a dipole-dipole interaction itself. If no, it's just dipole-dipole. Okay. If there are nothing that is polar or ionic, then we're stuck with dispersion forces. All right. And they are induced dipoles. All right. The only other thing that's missing from this is an induced dipole interaction, where induced dipole-dipole interaction, where something polar causes something nonpolar to temporarily have a dipole. Okay, but this is just kind of summarizing. Okay, I definitely thought we would get way past where we were, but we're good. Like, I thought we'd be here at minute 20 in class. Comparing the magnitude of intermolecular forces, this is important, but remember, if the sizes are different, this gets real hard. So here we go. This is the easy one here. And this is most commonly tested, so don't panic. If the size of the molecule is comparable, meaning they're similar, all right, then hydrogen bonding is great. Dipole-dipole in the middle, and LDF the weakest. In that order. You all right with that? Okay, if molecules vary in size, then it gets harder. So it's more difficult to compare the relative strengths of the intermolecular forces, as LDFs could be more significant than dipole-dipole and even hydrogen bonding. You would never, ever be asked a question about them where it would be the reverse of this unless they also presented you data. Because you can't just know every single thing. You'll have to have data, then you'll have to support it by saying, oh, hey, even though this was polar, this one must have stronger LDFs. You all right with that? This one will always be accompanied with data or data, whichever you like to say. Okay, so another way to say this part right here is things with hydrogen bonding have high melting point and boiling points, right? Medium and low. All right, I see a lot of pencils moving, so I'll just wait a minute. Who's Tim trying to flex on over here? It's Isaac. It's the two most perfect people looking in this class, and they're fighting.
Me and David?
Yep. Now that I didn't say perfect singing. All right, I'm moving on in 5, 4, 3, 2, 1. Okay, don't write anything yet, but now that we know all this crap, and we've talked about melting and boiling point extensively, but there are a few other things that intermolecular forces affect. So the strength of attractions between particles can greatly affect the properties of a substance or a solution. So here we go. These are the properties that you need to be able to explain how intermolecular forces affect them. So we have done that one. It's not, hey, don't clap right now. This is the most important one. Vapor pressure. I read this, I was going through because I was read ahead and I'm like, oh, you know what? I don't think I talked about water vapor pressure, but I never really talked about what vapor pressure was, right?
Yeah.
Okay, so let's go here. I have Erlenmeyer flask.
Has this been graduated?
Nope. This is an ungraduated one.
What a beautiful drawing.
Thank you. It's either that or a space reentry capsule. All right, here I have a liquid. Every liquid, yeah, it could be one of those. Every liquid will always have some of its own molecules above it that are vapor. They just always will. Sometimes there's not very much, and that's when the liquid's cold. And sometimes there's a ton of it, and that's when the liquid is hot. And boiling point is when the atmospheric pressure and the vapor pressure become the same. So vapor pressure is the measure of how much vapor would be above here, above the gas above the liquid. So think about this. If this liquid is holding on to itself really tightly, what would that do to the vapor pressure above it? It would lower it.
Wait, so how is there like this obvious line where the water starts and stops? So
It's called the liquid gas interface. How is it? It's because in the liquid, the intermolecular forces are dominating at that temperature, but there's still some that have enough energy to leave, just not very many of them. I don't know. Say that again.
Just when because they're all vapor, it's just they're all come together. All the ones.
I know what he was trying to get at.
Close together, they all stay in the same place.
Yep, they all stay together because they're attracted to each other. But one of these, one molecule can randomly get enough energy to leave the system. And that's why things evaporate. But how do we speed up evaporation? We add heat. Okay, now going back to this, we said if they're holding tight, the vapor pressure is low. So, well, whatever. So high IMF equals low vapor pressure. Now, vapor pressure and boiling point are extremely similar and related to each other, right? They are a high IMF equals a high boiling point, right? So they are inverses of each other. Vapor pressure and boiling point are inverse. Well done. All right. Volatility in the next 10 seconds. No. You think so. You're like, wow, that's really volatile. It means how easy it is to evaporate. Now, what that has to do with exploding, flammable things are very volatile. So they evaporate, and then the gas finds a source. Then you get an explosion. But if it's not very volatile, you could have a flame right here, and it would never light the liquid on fire. You have to have it evaporate, and then. Okay, we'll pick it up here because I think we're definitely out of time. We're pretty much done with this chapter, in case anyone has wondered. All right, peace out, online kids. Love you. Hope you're well.